There are many well-known musicians, from Billy Joel to Kanye West, with a perceptual condition called synesthesia, which allows musical notes to be perceived visually as colors. Those of us who do not perceive music this way can always rely on digital signal processing to provide some interesting and colorful visualizations of music. This video will describe the steps involved in using digital signal processing to create visualizations of music and the information that can be gained from these visualizations. I will demonstrate in Python how easy it is to create these plots for yourself. The backbone of digital signal processing is the Fourier Transform. The Fourier Transform is a transformation of variables, which takes a function of time, seen here, and transforms it into a function of frequency, seen here. This is what allows us to see what frequencies are present in a signal and at what intensities. In this plot, called the spectrogram, time lies in the horizontal direction, frequency is vertical, and the intensity at which a frequency is present is represented by its color. The frequency domain is where all the interesting information in a piece of music is contained. Musical notes are defined by their fundamental frequency, as seen on this chart of piano notes. But subjective measures such as judging the quality of a played note have more to do with the higher harmonics. This is a plot of the same trumpet note being played 8 times. The main difference between each note is the activity in the higher harmonics. Generally, notes with more activity in the higher harmonics are subjectively judged to be of better quality. Another interesting way to plot this data is to look at the power spectrum. Here, the power of each frequency present in one trumpet note is shown. It is slightly unexpected to see that the higher harmonics contain more of the signal's power than the fundamental frequency. In this plot, you can see that the second harmonic has the highest power, with the fourth and fifth harmonics also appearing above the fundamental frequency. This is a feature of the resonances created within the trumpet, amplifying the higher harmonics. Now I will demonstrate how simple it is to create these plots for yourself using Python. Python has an incredibly extensive graphing library, and the signal processing functions that you need are actually packaged inside the graphing library to make Python by far the most user-friendly choice for this application. The first step is to read the wave file, which we do on line 14. We then take this wave data and pass it into the spectrogram function, which processes the data and populates our plot all in one step. You can set limits on the x and y axes in order to zoom in on any interesting parts of your plot. For example, you could take a closer look at the fundamental frequency or zoom in on one particular note. Creating the power plots is just as simple using the PSD function from the plotting library. Here, PSD stands for power spectral density. It is important to note that looking at the power spectrum only makes sense for repeating signals such as one individual note. On lines 15 and 16, the time values are set to the beginning and end of the note of interest so that only this time interval is evaluated by the PSD function. I hope that this brief signal processing demonstration and Python code will allow you to make some new discoveries about your favorite music and find some new ways to appreciate it. Thank you for watching, and you can subscribe for more of our videos.